Welcome to our research entitled Interpretable Concept-Based Deep Learning Framework for Multimodal Human Behavior Modeling. As an indispensable part of psychology, psychiatry, and human-computer interaction, emotion recognition systems, or a border field, effective computing, are designed to detect and interpret human behavior states. The recently released European General Data Protection Regulation requires emotion-related models as one representative of high-risk AI systems to be sufficiently transparent and interpretable. However, interpretability in general in effective computing is an ongoing research, mainly due to the inherent ambiguity and complexity of human behavior. Previous effective computing is composed of feature-based models and end-to-end models. Feature-based models map only the human-understandable pre-processed features to task labels, risking the loss of valuable raw data information. End-to-end approaches improve performance by learning a deep model directly between raw input and labels. However, these end-to-end approaches often lack explainability in both single-task and multitask learning scenarios, leaving the decision-making process as a black box. Therefore, we proposed a concept-based interpretable solution in this paper, combining the advantages of well-understandable feature-based models and the state-of-the-art performance of the end-to-end models. In addition to black box models, previous works have primarily relied on map-based explanations, originally developed for object detection and localization. These approaches explain predictions by highlighting important regions or parameters, but fail to provide domain-specific insights into the decision-making process. However, due to the interdisciplinary nature of effective computing, the explanation should be designed to serve the stakeholders, such as psychologists and cognitive scientists. For these people, explaining effective signals by localizing one's body region is not enough, especially with complex visual behavior, where the opposite indicators, like AU12 and AU15, may appear in the same region of the face. It is even more problematic in multimodal explanation, where the alignment and co-learning of the spatial and temporal explanation is especially challenging. To this end, we propose the attention-guided concept model, which not only localizes the important region of input, but also identifies the indicators or concepts that contribute most to the predictions. It creates trainable concept embedding for emotional indicators and learns their contribution to a given task in an interpretable, multimodal manner. To validate the efficiency of our model, we first evaluate its state-of-the-art performance on well-established facial expression recognition datasets. After that, we further demonstrate its downstream generalizability on a real-world human-human interaction task. In the rest of this video, we provide demos of AGCM prediction and explanation with both the spatial and multimodal conceptual explanation. In this example, the model first recognizes surprise because of the high contribution of AU1 and AU25. Then, emotion prediction transfers to happiness due to the high activation of AU12. Finally, the model successfully predicts the emotion downregulation as the deactivation of most of the concepts. To demonstrate the robustness of the conceptual explanation, we further evaluate the model in the complex scenario of occlusion. Our experiment shows that AGCM accurately focuses on the non-occluded regions and predicts the task label based on the available concepts, demonstrating its robustness in handling facial expressions with hand-over-face occlusion. In this example, we show the original video and frame inputs alongside the AGCM's emotion predictions, spatial explanations, acoustic conceptual explanations, and the top 3 visual concepts. Initially, the prediction remains in a neutral state due to the deactivation of most facial concepts. Subsequently, the prediction transitions to anger, driven by the high contribution of AU4 and elevated intensities of both loudness and pitch in the audio signal. Finally, the prediction shifts to surprise, attributed to the strong influence of AU1, AU2, and AU25. This example highlights AGCM's ability to provide human-interpretable explanations while maintaining robust emotion prediction accuracy. To further illustrate the usability of AGCM's prediction and explainability in downstream effective computing tasks beyond FER, here is an example of a human-human interaction task involving engagement estimation. As part of the visual explanation, we visualize conceptual insights, such as head orientation and
Oui.
gaze direction.
Pareil, je connais la musique,
A
mais je connais pas le
conceptual
film.
explanation of high engagement includes forward head orientation, direct eye contact, an engaging smile, and active conversational interaction. In contrast, low engagement occurs when the subject's attention shifts away from the conversation, resulting in decreased forward head and gaze concept activations. Engagement is regained when positive facial expressions and acoustic concepts, such as tone and vocal intensity, become prominent, signaling the subject's renewed focus and positive emotional feedback. These results demonstrate that AGCM is both generalizable and expandable,
D'accord.
providing human interpretable conceptual explanations for real-world effective computing applications beyond FER.